Try to solve one of the questions from today's tutorial test. Okay, so I think the first thing that I think one of you will get at least 4 marks from, it will be trying to do the derivatives for the function of which our f of x. I think that's where you can score 4 marks. F of x, I'll just skip through calculating derivatives because by now you guys have done a lot of math. You know how to differentiate, right? You know this, right? Let me do these are our derivatives, and then let me see this expression, trying to simplify it, and I'll evaluate it as x is equal to 0. Okay, cool. So let's try to find first derivative of if I derive this guy. I think I'll probably go use a chain rule because it's more of like it's cos x then squared inside, so I'll derive outside then inside. You get the point. So if I do that, this 2 you'll see it like that, cos x sine x, and if I evaluate at 0, so sine 0 is just going to yield exactly 0. Okay, yes, to be 0. Move to the next step. Let's try to find f second prime, and then I think this would be more of like a product rule. I'm not going to actually go to like technically trying to help you do it because I think we did a lot of these things in differential equations. So differentiating this guy now becomes that. Then if I try to evaluate it, it's 0, then I'm going to get negative 2. Okay, cool. Then I think we should continue again. Let's try to find the third. Many people don't like writing 3 things here. They want to write exactly 3. Then if I differentiate again, so end up getting an 8 cos x sine x. Obviously, doing the math in between here is not going to be awarded since this is not differential equation cos. And then if I evaluate this or substitute x inside it, obviously you see this sign will make everything just become 0. Then let's try f the fourth derivative. Fourth derivative will be 8 upon cos squared minus sine squared x. I hope you can see the pattern. Okay, then if I evaluate here, I'm going to get 8. Then I'll do for f fifth derivative, it's going to be negative 32 cos x sine x. If I evaluate, I'll get a 0. Remember, evaluating at 0. Then I'm going to do a sixth derivative. A sixth derivative is going to the expression is going to be negative 32 cos x squared minus sine squared x, of which you see the pattern by now, negative 32. Okay, cool. So if you did at least this, I think you can now score at least 4 marks. Let me say 1, 2, 3, 4. I don't know which one they didn't count, but on the memo, I think they gave you guys at least 3 marks from that. I mean 4 marks. From this, it's easy to notice that all the odd functions are 0 at if they're evaluated at 0, or I mean odd order, if that makes sense. All the odd order derivatives. Yeah, let me just write that English down because it doesn't sound right to say odd order derivative. They equals to 0 at x is equals to 0, right? And then I'm just saying the observations that I'm saying, and then even odd order, derivatives, they have alternating sign, right? We can see it was negative, it was positive, it was negative. So we hope that thing continues like that throughout. And then we're going to use a Maclaurin formula, of which it's, let me just go back to this pen. Maclaurin, okay, fx is equals to the sum, forgive me, I very not good handwriting, is equals to 0xn fn at 0. That's Maclaurin is, right? But we're only going to do only, let me make that one red because it was important, only for what? For even derivatives. Why? Because the odd ones, we did say they are zeros, right? So if we do that, we're going to see something. Remember, only doing for odd, right? It's going to be 1 plus f. Okay, I'm just evaluating that Maclaurin series, right? 4 0. So there are terms in betweens, but we just ignore them because they are 0, right? Because we did say that we only focusing on odds, of which the one that yield things that are interesting, at least to us for now. So we can substitute the values from the values earlier, of which we have from that table that we did. Now we can say cos²x is equals to 1 plus negative 2x² all over 2. Remember, I'm substituting these values because they're the one that are showing in the Maclaurin, right? Plus 8x4 factorial plus 32 . You notice I'm only still focused on the even ones, right? Because the odd ones were only giving zeros, so they're just zeros throughout. So this thing continues. Okay, from this we can also make some observations again. The easy one, let's look at the denominators. Remember, this is like okay, the denominator follows a pattern of 2m, right? Because this is like 1, then this become 2, then become 2 times 2, this become 3 times 2. This is a pattern for denominator. That's an observation that we are doing right now. Okay, that observation that powers are even, you see. So we're hoping continues forever, and it's going to be even powers again. So for powers, powers of x are even, so they follow this pattern, right? And the last observation to make is going to be the coefficients. The coefficient follow a pattern of -1 because of alternating signs already. It's more of like it's a redundancy because I did make this observation before. They follow this pattern, the coefficients, all right? Cool. So I actually have a calculator. If you just keep on putting these, looking at coefficients at these guys, right? Let me go back at these guys. So we're trying to find the pattern that they follow. This is the pattern they follow, right? So if I can try to substitute let me say 3 for this guy, try and find a coefficient for here, just calculate for 3, I'm getting -32. So these are a very good observation to make. I think they are vital for our conclusion. So if we know all these observations, we can actually just write them down as just one beautiful thing. So we can say cos x does look like this. Remember now, because we are going up to infinity, this is not really an approximation, it's actually equals to this, because remember, the more terms you can take, the more accurate your approximation is. So if I can take all the terms, let me say to infinity, that means it's actually no error involved in that. So if you ask what I'm doing here, I'm just writing all our observations to one beautiful looking thing, because you already know that cos²x is equal to this, but you also spotted a pattern here. That means you can write that thing in terms of sums here, right? That's a very good achievement. So now we have a sequence on it's a sequence. I don't say series. A sequence am of which is just whatever this thing that is there, -1m, 2m minus 1 x 2m all over 2m factorial. Right, now we want to find if this sequence converges or diverges, and we're only interested in this part, in diverging or converging, because obviously this guy converges, and if this guy converges, so this whole thing mainly depends on this guy for divergent and convergent. So if this guy converges, this whole thing converges. If this guy diverges, you get the story now. Okay, so we're going to use our ratio test. Remember ratio test from calculus 2a. We used to do this with people that I was with in my class, like that, but I think it's a universal thing, isn't it? So we're just substituting the next term over the previous term. That's what translates to in English. Then I'll write a lot of stuff, or just me substituting. Let me just pause to make a video. So if you meet something, let's try to explain what I did here. So this is exactly the same as the other one, right? Just that now the next term, you see, we have this for all the but it's on this side. I just flipped it upside down. The reason why I flipped it upside down here, it's because I'm trying to divide by it, so it's same as flipping it upside down. So this guy technically looked like that guy, but this is the next term, previous term. Then you know this thing, we've done it with you guys before. Okay, so just to save our time, then here it'll be a lot of cancelling of terms. Hopefully you'll be left with something that look like 2x all over 2m plus 2m plus 1, and there'll be a lot of math involved here, which we're not really interested in. I trust you with. It will be just terms cancelling. I don't know how, but yes, they do, because you know math, right? And then let's try to take the limit as m goes to infinity. And if we take the limit as m goes to infinity, remember the reason why I'm not actually being explicitly in terms of what am I doing is because most of the things that we're doing here is just those convergent tests that we did on calculus. So it's really not numerical analysis. Remember, the cause is numerical analysis. So if you push everything at zero, this below part will get very big. That means this thing will just goes to 0. Okay, so our limit now is going to be 0 and is less than 1. This is my conclusion, by the way. Got it from previous term. Also ratio test says this thing convergence. Okay, cool. For x, for all the x, right? Yeah, let's move to the second question. Okay, on the next question, I think it's an error question. Let's remember some easy things to remember. Okay, fx can be approximated by some polynomial of some degree, but to actually have it like equally, you need to add some error, because it's a polynomial is approximation, right? So you need some error to actually counter, because I want to say this, these guys are not really equal, but they can help you. But with adding the error, you can actually change that to that. Okay, cool. Let's look at the second question then. So the question now is this one that we're working on, and this was the one that was actually had some typo error in your test, but I think we were able to resolve it. Let's try to see what we can do. So technically the goal here is The goal is to find the smallest non-zero integer for n to ensure that to ensure this part, right, of which this is what the question is saying. So let's try to, the first step we'll try to also bound our error. Okay, bounding is literally putting something in both ends. I think that's what it means in English. 2n plus 2. I'm just copying, if you can see there, because I don't know how to write psi. Okay, let's take that. Sine psi again. It doesn't even look the same, but yeah. 2n plus 2. Yeah. Now we'll set x is equals to 1, and now we'll take the maximum. Right, we're finding a max where psi is between 0 and 1. I think this was part of things that were said on our very beginning statement. Okay, of our error. Then 2n plus 1. Also remember, we're taking absolute value of our error plus 2. So trying to find the maximum value. Psi is between I'm supposed to do that here to make it clear, and both of these ends are included. When you're writing these math things, you need to be technical, because any of these things can actually cost you a mark, because not including what is supposed to be included is really saying you don't know what you were doing. Oh, my psi is not really look nice. Okay, cool. So yeah, and then my next goal, we're trying to maximize our cos psi, sine psi over an interval, right? So maximum we use to over interval. We use to differentiating, then after differentiating you can actually find the turning point. That's what maximum are from your first year calculus, right? And then if I differentiate this, I get negative sine squared psi plus cos squared, right? And this equals to 0. So we now know that this thing reached a maximum at 0. Oh no, I mean to say, to get a maximum you need to find a derivative. That's what we did. Then we're literally saying the slope is 0. That's what I'm saying here. So after finding, and then I have to find where is actually the slope is 0. And if you're wondering how I did this, obviously I'm going to use product rule. I'm just not going to do differential to keep the video shorter. Set this thing to equals to 0, then if I set this thing equals to 0, then I'll have sine squared psi is equals to cos psi. Forgive my psi's, please. And then you can actually divide by this on the other side. Then you'll have to have tan squared psi is equals to 1. And then because it's a square here, we can just we can try to find critical point by saying tan psi, I don't know how they say it, plus or minus 1, because I'm trying to get rid of that guy. Alright, and then if you try to compute that on your calculator, you get your psi equals to plus or minus 0.7854, depending on how many significant figures you want to have. And if you just look on your calculator, that's almost the same as pi divided by, pi divided by 4 at least. You can just call that pi divided by 4, of which also what to notice that we're only looking at, that's only for 1. We didn't check for negative 1. Okay, if we try arc 10 negative 1, of which will get us negative 4 over, and then that one won't be on our interval 0 and 1, so we just don't mind it. So from then, now we know that maximum of obviously using absolute sign, then psi occurs at psi is equal to, let me just put pi over 4, right? And then now our next step will be evaluating cos psi sin psi at critical point. Let me call them key points. Like at 0 we're going to yield 0, at 0 we're going to get 0. Let's try it at 1, we're going to get 0 0.4546, and at something else, I think that's one that we just computed at 0.41784, that pi over 4, right? 54, we're going to get we're getting 0.5, right? And then yeah, so from doing all this plugging in, we literally see that on our interval the max that we get is usually 0.5. So let's move. So what I'll be doing technically right now, I'll be just writing by trying to maximize this guy on this interval. Remember it's closed here. Rn is equals to 2 to n plus 1 all over 2n plus 2 factorial. And I think what we had here, let me go check the question. Oh yes, also trying to find the maximum between this interval, remember here, 0 and n of this function cos and then sine psi. Remember we already sorted this guy, we said the max, so this whole thing, the maximum there is going to be 0.5. So we'll have 2n plus 1 all over 2n plus 2, 1 over 2 for that 2.5 story. Okay, if easier, I like to change this guy to make him to -1. If it's -1, this power -1, so you can see that just cancel that guy, so we'll have this, right? So I want this thing to be less than 10. That was the question, -5. This is our error, right? I want it to be less than that, right? I'm going to have to find the right n. So technically what we're doing now is just solving for n. So the answer will be n should be greater than 4. So I'm obviously skipping math in between here, but I hope it doesn't confuse that much. So yeah, that's it for the test. If you're able to do that much, you're going to score at least 15 marks. I don't know, there was 15 marks overall. But also on this video, also do a small animation video on how errors look and all these Taylor series. So just, I think from now on, I'm just getting back to my computer. So this is a Python program that kind of show you that if you add more terms, you get. I'm plotting this function and versus its polynomial guess, if it's say guess or approximation, and then from then you can see as we add number of terms how it actually affects it. So so I hope you can see my screen here. So what is happening, I think I should just do full screen. This is number of term or Taylor order. You see here it's increasing, and you can see as I increase number of terms, this thing gets very closer and closer to the actual function. And the blue one below here, it's an error function. So the error function is also changing as you move along axis. You can see that as you increase the thingy, the Taylor order, the error is getting smaller, actually approaching 0. And you can see that things are getting very closer it's getting closer to the actual function that is trying to approximate. Now I'm doing the same thing for sine. You can see that whatever that I'm using to approximate here, as I'm increasing the Taylor order here, or number of times simply, it's getting very close and very close, and the error is kind of dying. I could also plot for another function, but the code, you can just see it there. You can just rewrite it, or just, I don't know, put in a description. Not that bad. Yeah, thank you. I think that's the end of the video.